In section 8-4, we're going to be talking about vectors. And if you remember, vectors are like array, and they have a terminal point and an initial point. And the initial point is where it starts, so right here. And the terminal point is where it terminates, so where it ends. And remember, when you're graphing a vector, you're going to rise a certain value, and you're going to go over a certain value to actually get to the terminal point of the vector. So when we did vectors earlier, when we did navigation, we drew vectors from head to tail. So if this is vector A, then if I wanted to add vector A to vector B, then B would go at the end of A, and the result would be from A starting or ending at where B ends. So this would be vector A plus B. So the big thing to remember is just vectors go head to tail when adding them. So moving on to the component form of a vector, if we have vector v that has a starting point or initial point of x1, y1 and a terminal point of x2, y2, then we can write the vector in the following way. You can take the difference of the x components, so you're going to take x2 minus x1, and then you're going to subtract the difference. You're going to take the difference of the y components, so y2 minus y1. So this is the formula that you are going to be using to find the vector that you're going to be drawing. So here's a little visual illustrating what this formula is all about. Remember, when you draw a vector, you have a horizontal component, so how far over you go, and then how far up you go, and that's how you graph your vector. Well, this distance right here, the distance from x1 to x2, is this right here. And then how far up you go, this distance here, is the y2 minus y1, or there. So it's basically just showing you how to draw your vector. So illustrating this concept is example 1. You're going to find the vector v with initial point of 5, 4. So this is like your x1 and this is your y1. And then you have your terminal point 4, 8. So that's like your x2 and your y2. So to find vector b, all you're going to do, and remember, vectors that are in component form have these weird little like greater than or less than signs. All you're going to do is just take the difference of the coordinates. So you're going to do x2, which is 4. So you're going to do 4 minus x1, which is negative 5. And then you're going to do the same thing with the y. So you're going to do y2 minus y1, which is 4. And then you just simplify, and that's your vector in component form. So you end up getting, what is that, 9, 4 as your vector. So in the second example, we're going to graph vector v. So we're going to take its initial point and we're going to graph its terminal point. So I'll do that now. So I went ahead and graphed negative 5, 4 and 4, 8. And when I draw the vector, so it starts at here and ends at 4, 8, that's what it would look like. And what I want to show you is what this 9, 4 represents. So 9 is the horizontal distance I'd have to travel. So this is a distance of 9 from the starting point to the end point. And then I'd have to go up 1, 2, 3, 4. And that basically represents the vector because I go horizontally 9 and vertically 4. So the vector is 9, 4. So in this last example for this type of problem, if W is a vector that's 2, 5, so that means that you go horizontally 2 in the x direction and up 5 in the y direction, and it has an initial or starting point of negative 1, 3, we want to find what its terminal point is. So let's graph negative 1, 3. So what I've done in purple on the graph is graph the point negative 1, 3, and I know if the vector is 2, 5, that means from this starting point, I'm going to go over 2 horizontally and up 1, 2, 3, 4, 5. So that means that when I terminate, I'm terminating right here on this point. So that means that the terminal point would actually be 1, 8. And so that's where the vector would terminate, so that it would look something similar to this, to have the components 2, 5. So next we're going to be going into the algebraic operations of vectors. So adding, multiplying by a scalar, subtracting, and so on. So the first example, we're going to have vector u have components 4, 5, so you'd go over horizontally 4 and then up 5 vertically. And vector v has coordinates negative 3, 4, so components negative 3, 4. So what I'm going to have you do is add the two vectors. So all you're going to do is add like components. So all you would do is take the first component, the 4, and then you're going to add on the negative 3, and then add the other components, the 5 plus the 4. So you end up getting 1, 9 would be your result. Similarly, if I went ahead and had you multiply vector u with components 4, 5 by 2, all you would do is you would take 2, the scalar 2, and multiply it by 4, 5. So when you distribute that out, you would end up getting 8, 10. And in this last example, let's take vector v and vector v having components negative 3, 4, and add that to opposite of vector v. So if I take opposite of vector v, that turns positive 3 and negative 4. So when I add like components, adding the 2 there and the 2 there, I end up getting 0, 0. And this is known as the 0 vector. Alright, so let's move on to the magnitude or length of a vector. So the magnitude of a vector is the vector's length, or the modulus, if you will. So here's the formula to find the length of a vector with components a, b. So if we have vector v with components a, b, then the length or magnitude is the square root of each of its components squared and then added together. So we have the square root of a squared plus b squared. It's kind of like finding the modulus of a complex number. So in this example, we have a vector that has components 5/13 and negative 12/13, and I want you to find its length. So I'm hoping you're seeing similarities between all of these formulas, whether it's in polar mode or it's an imaginary number. You're finding the distance kind of using the Pythagorean theorem. So in this case, we're going to go ahead and take the square root of, this would be a, and this would be b. And I'm going to take 5/13 squared and add on negative 12/13, and I'm going to square it. So when I go ahead and square that, I get 25 over 169 plus 144 over 169, or if I simplify that, I end up getting 169 over 169. And when I square root 1, I basically just get 1. So the length of this vector has a length of 1. And it's also known as a unit vector. And a unit vector is a vector that has a length or magnitude of 1. So I am going to write this as a unit vector because it has a unit or length of 1. So the next thing we're going to be doing now that we know its length is we want to know the direction it's going, so at what angle it's at from the x-axis. So here's what the formula is. So it's similar to the formulas that we've already developed for this chapter. So if you're given a vector with components a, b, then the angle formed would just be tan inverse of b over a. Here's an example. So let's say I graph a vector that I go over a and I go up b, and I'm starting at the origin to graph it. So my vector would look something like this. So if I want to find the angle formed with the x-axis, I would use this formula right here to get the angle. I would use tangent, which is opposite over adjacent, and to get the angle, I'm using inverse. So that's the formula tan inverse b over a. Alright, so let's say I have this vector that has components negative root 3, comma 1. Now negative root 3 is approximately negative 1.7. So if I were to go ahead and graph this, I'd go left negative 1.7. So let's say this is negative 1 and negative 2. So I'd go left negative 1.7 and up 1. So I'd be about right here, let's just say. So my vector, I'm going to start all my vectors when I draw them from the origin, would be right there because I have my root 3 component and I have my 1 component. So with that said, now I want to find the angle. And that angle is measured from the x-axis. So I need to find that angle. So all I'm going to use is theta is equal to tan inverse of b, which is 1 over negative root 3. So when I rationalize that, I'm going to get tan inverse of negative root 3 over 3 rationalized, which is on the unit circle. So when looking at the unit circle, tangent is negative root 3 over 3 at 5 pi over 6, and it's also at 11 pi over 6. So here's the deal. So I get two answers, 5 pi over 6 and 11 pi over 6. But the deal is I have to figure out which angle I actually want when I look at my vector. There's my vector right here in quadrant 2. So my answer, my angle, would be the one that's in quadrant 2, which is 5 pi over 6. So that's theta. So now we're going to look at a different form of vectors. We were looking at the ones in component form, which had those little like greater than or less than signs, it kind of looks like. Now we're going to be looking at them in terms of I and j. So vector v that has in component form just the little bracket or alligator things, if you will, AB, components AB, is equivalent to writing it with a plus sign in between the A and B, but then you put in the I and the J. So that would be its equivalent form of AI plus BJ. So here's an example. So in this example, you're asked to write vector W that's in component form. I should probably make this guy look more like a greater than sign. And I want you to write it in IJ form. So all you're going to do is you're going to take the first component, the 4, and you're going to do 4i, and then put a plus sign, and then you're going to take the next component, the negative 3, and you're going to have minus 3j. So if I were to go ahead and simplify this, I would just write it as 4i minus 3j. So it's really quite simple to go from component form to IJ form. You just basically put an I and a j next to each of the components and a plus sign in between them. So in this next example, if vector u is equal to 5i plus 3j and v is equal to negative 4i plus 6j, I want you to find each of these. So you're going to take 2 times vector u, so you're going to get 2 times the 5i plus the 3j, and you're going to subtract off vector v, which is negative 4i plus 6j. And so you just distribute the first thing out, so you're going to have a 10i plus a 6j, and then minus a minus turns plus 4i, and then minus 6j. So combining like terms, you get a 10i minus that's not like. We're going to get a 10i plus a 4i, or 14i, and then combining the j components, you would end up getting 0. So the final answer would be just 14i. So in the second example, I'm going to have you find the magnitude, remember absolute value means magnitude, of vector v. And some people really just like component form a lot better, so if you like dealing with component form, that's fine. Just make sure your final answer is in the form that it started with. So you could write that as 5, 3 if you really want, and you can write this as negative 4, 6. So remember, finding the magnitude, it's the square root of a squared plus b squared. So I would just go ahead and plug it in. I'd plug in the negative 4 and I'd square it, and then I'd plug in the 6 and square it, and then simplify. So I basically get the square root of 16 plus 36. So I end up getting the square root of 56, which simplifies into 2 root 13. So basically the length of this vector right here would be 2 root 13. I just saw a mistake. It wouldn't be 56, it would be 52, and then that would be 2 root 13. So the last thing is we're going to be finding the horizontal and vertical components of a vector given the magnitude, so its length and its direction, so what direction it's heading from the positive x-axis, theta. So we're going to let v have components AB. So if I were to draw a vector v, let's just make it right here. So I'll call this vector v. It has a certain magnitude, so remember magnitude is the same thing as absolute value, and its components are over A, so its horizontal component is A, and its vertical component is B, thus A, B. So the horizontal component A can be rewritten in terms of theta and its magnitude. It is equal to the magnitude of the vector, so vector v, the magnitude, times cosine of theta. And to get b, so this guy right here, b is equal to the magnitude of the vector times sine of theta. If you remember back to converting from polar to rectangular, remember the x was equal to r cosine theta. So remember, r is the same thing as the length or the distance from the pole. Well, it's the same thing. V is the magnitude or distance from the origin right here. And then since the coordinate right here is related to the x, it's cosine. So I'm going to put right here, this is equal to the magnitude of the vector times cosine of theta. And then this one is equal to the magnitude of the vector times sine of theta. So I can write vector v, this vector right here, in terms of its components, in terms of its magnitude and its direction. And this is how I would do it. In component form, vector v can be rewritten like this. Since a is this, I'm going to replace it with the magnitude of v times cosine of theta. And then the second component would be the magnitude of v times sine of theta. So these are two equivalent things. One is just knowing its length and its angle, and the other one is just knowing its horizontal and vertical components. So this would be component form. I can also write this vector in ij form. So what I could do is I could say, or, if you wanted to write vector v in ij form, it would be the magnitude of v times cosine of theta I, because remember you put the ij, plus, and then you put the next component, vector v times sine of theta j. So these are equivalent. This is just considered ij form. So the final example for the evening, we're ready. Alright, so vector v has a magnitude of 4. So remember, magnitude is the absolute value, so I can write the absolute value of v. That equals 4. And the direction, it's pi over 6. So if I were to do a little sketch, so it goes along the angle pi over 6, or 30 degrees. So this would be a pi over 6 angle, that's theta. And then its length is 4. So what our goal is to write that in component, or ij form, not component form. So the form we're looking at is this one right here. This is ij form of a vector. So when I go ahead and do that, I'm going to write vector v equals, and then I just plug it in. I already know the magnitude. The magnitude's 4. That's that right there. And then I'm going to multiply that by cosine of theta, which is pi over 6, and then I, plus, and then I go ahead and plug in the magnitude, which is 4, times sine of theta, which is pi over 6j. So now I just go ahead and simplify. So vector v would equal 4. Cosine of pi over 6 is root 3 over 2. And then that's the I, plus 4 sine of pi over 6 is 1/2 j. Oops, I don't need the sine, because sine of pi over 6 is 1/2. So then I can simplify. So this ends up becoming vector v as 2 root 3 I, plus, and then 2 goes into the 4 twice, 2j. So that would be my vector. I would go over 2 root 3 horizontally in the I direction, or the horizontal direction, and up 2 in the j direction, or the vertical direction. Alright, that is it. Sorry it was so long. Have a great evening.